In this example, we are going to look at a satellite that is in circular orbit of radius r about the Earth. So when you think about satellite, right, I think the first natural satellite that you learn about that should come to mind is the moon, right? You know, especially in primary school, there was what my teacher told me the first thing. Oh, you have a moon and the moon travels in a circle around the sun like that. Wow. Okay, but let's observe the path of the moon, okay? So you can see the satellite is tracing a circular path around the Earth. Now, if this moon is actually moving and you think about the velocity, the direction of V is always changing. And because the direction of V is always changing, we need something to provide centripetal force. And that something is your good old gravity. So if you look here, you will see that there's an action-reaction pair, right? The Earth is actually pulling the moon, keeping it in the circular orbit. But there's also obviously the moon pulling on the Earth. And that's how we get tides, you know, the water tides in the sea, all right? So will something similar happen for satellites? Let's see. Okay, normally when it comes to satellites, man-made satellites, you know, the one that you use for telecommunication, to watch your astro, to get your internet, all right? So this kind of satellites, right, will also operate in the same way like the moon, and the attraction force or the gravitational force provides the necessary centripetal force so that this satellite can move in a circle. That was the concept you learned in circular motion, right? That in order for anything to move in a circle, we need a centripetal force. So this is where most of the circular orbit question will start from. This is the starting point, okay? So when you have a satellite in circular orbit in radius r about the Earth of mass m, okay, Ken, and the mass of the Earth may be assumed to concentrate at the center. If it's not concentrated at the center, then you cannot use Newton's law of gravitation. Then it's a different story already, okay? But today, and for this syllabus, we're going to stick to that. So I'm going to call the mass of the Earth as capital M. Let me adjust the... Okay? And the mass of the satellite as lowercase m. It says here, show that the period of the orbit of the satellite is given by this expression. Let me tell you something. In the past year questions for this chapter, right, they have to throw you random equation one. Sometimes you see before, sometimes you never see before. I'll give you a few examples. If you look at this one, walao, we got density one. Yeah, lor, they can give you anything. But don't worry, I learned this pro tip from my student who do a lot of past year, so we learn from their experience. The student said, whenever I see a proving question for gravitation, definitely I can use the relationship or the idea that gravitational force provides the necessary centripetal force. And that's right. So you start off with this sentence, okay? Gravitational force provide the necessary centripetal force. And because of this, you can write the equation Fg is equal to Fc. Always start your proof by this expression. Don't go and write some other equation that you memorize, and then you will lose mark in your proof, okay? So now we are going to write down the equation from Newton's law of gravitation. Gravitational force was G, mass of the planet, mass of the satellite. Because the force of attraction is between the mass of the planet, so the planet or Earth is attracting the satellite. So this is your Fg. But the satellite is also attracting Earth. It's just that Earth has much more mass, so you don't really see the effect of the satellite besides, I mean, satellite definitely not lah, but moon, maybe just the tides, okay? The ocean waves. So it's the attractive force between Earth and moon, or Earth and the satellite, okay? Divide by the separation square, r square. So the radius or the separation is r, okay? And then we are going to put in the equation for centripetal force. So now when it comes to centripetal force, you have two equations, right? The first equation that you can use is centripetal force is mv square over r, okay? Where v is the tangential speed of the satellite. So this value of v is this v. Okay, and r is the radius, the separation, and m is the mass of the satellite. So if I use this equation, I will have a little bit of extra step in order for me to find period. Not cannot, but a little bit extra. Okay, so the extra step needed here is to think about velocity in terms of distance over time, because the speed of the satellite is constant. So if you stare at this satellite long time, you will notice that, hey, you know, it's traveling in a circle. So the distance traveled is the circumference of the circle, which is 2 pi r. So 2 pi r divided by the period, which is t. Because period is time taken, period of the orbit, this period of the orbit is time taken for one complete cycle. Okay, so this is for the satellite to travel one complete circle. Okay, one complete orbit. All right, so this one got 2 steps, and I don't know about you, but I kind of prefer to not need to use 2 steps. So I'm going to use the second equation, where centripetal force is mr omega square. Okay, and I know omega is equal to 2 pi over t. So it's up to you which one you want to use. Okay, I prefer to use the second one because it's a bit more straightforward, but up to you. All right, so I'm going to substitute mr omega square here. So whenever I substitute something in a proof, right, I will always write down for the examiner or the person that is looking through my working whenever I do some form of substitution. For example, I'm going to substitute omega as 2 pi over t into the equation. So I'll write at the side. Okay, and I will now cancel off my m because the mass of the satellite is the same. Miss, how do you know this one is the mass of the satellite? Well, this m is the mass of satellite because the satellite is moving in a circle. Because satellite moves in circle. If it's not moving in a circular orbit, then we won't have this question to begin with, right? So we'll take the mass of the object that is moving in a circle. This one. Moves in circle. So this gravitational force is equal to the centripetal force of the satellite. All right, that's why we use the mass of the satellite. Okay, so much talk, time to rearrange. Now I'm going to substitute omega as 2 pi over t. Okay, I will rearrange a bit. So from here, I'll bring down the r. I get gm over r cubed is equal to 2 pi. I mean, I'll just open up the square because I spot a t square here. Okay, so omega square will be 4 pi square divided by t square. And then you can rearrange, make t square the subject of your equation. This will be 4 pi square r cubed over gm. Proven. Okay, so t square is 4 pi square r cubed over gm. A few things to know. Where are the 3 marks? Mark number 1 is when you write down gravitational force is equal to centripetal force. Here is 1 mark. Okay, so this concept is where all the proving should start. Okay, the second mark is when I see gmm over r square is equal to mr omega square together. Let me change color to mark this. Together with this 2. This one is another. So all these are C1. No, this is an M1 mark. Interesting. Okay, I'll explain a bit what M1 means after this. This is a B1 mark. Okay, and finally, algebra. So basically, you should, whatever you substitute, the working should work out to this part of the equation. So this is A1. Okay, so whenever you look at mark scheme, right, you will only score this A1 only if M1 is also scored. So basically, if you never start with this, you will not get mark. Okay, what about B1? B1, this B is free. This is an independent mark. So if you don't get B1, so basically the candidate can get B1, M1, A1. This is 3 mark. Can get B0, M1, A1. This is 2 mark. Can get B1, M0, A0. This is 1 mark. But it is not possible for you to get B1, A1, 2 mark. These are the possible variation, or 0 lah, of course, didn't do anything. Okay, so this is what, whenever you see M mark, especially when you are marking your own paper, because you have to do quite a lot of that to improve your A2. No one's going to mark for you, okay? So look through the mark scheme. Whenever you see M1, just pay a bit of attention to it. It is always tied to A1. You don't get the M mark, you can't get the A mark, right? Okay, that's it. So when it comes to this proving, what we did was we substituted the value of, the expression for gravitational force and equating it to centripetal force, okay? And we arrive at this expression. A sidebar here about the expression. This t square is proportional to r cubed. Why? Because 4 pi square g and m are constants, right? G is the gravitational constant and m is the mass of the Earth. So these things are constant. This is actually Kepler's third law. Now in syllabus, you don't need to know the name, but you're already using it, so might as well just introduce it to you. This is Kepler's third law. Okay, it has something to do about how planetary objects move in a circle around each other, because this is not the only thing that's traveling in a circular orbit, right? The Earth is also moving in a circle orbiting the Sun. Okay, let's look at B. A satellite is in geostationary orbit, okay, and appear to remain above the same point on the Earth. So normally, whenever you see the word geostationary, this is the definition of geostationary. Appears to remain above the same point on the Earth. So basically, if you're standing on the Earth and you look up, the satellite is always at the same spot. If the satellite is not at the same spot, then it's not a geostationary satellite. Are they non-geostationary satellite? Yes, they are the remote control ones. We can use it to spy on people, or mainly used for tracking lah. Okay, so a geostationary orbit appears to remain above the same point on the Earth. Okay, what that means, if I can pull up this one for you, this satellite is not geostationary, because sometimes, okay, let me see if I can recognize, cannot recognize the planet. Okay, let me zoom in a bit. Okay, so sometimes the satellite is above here. Sometimes the satellite is above the ocean. Sometimes the satellite is above, I don't know, this one looks like Africa, America, I'm not sure. Okay, so depending on the rotation. This is non-geostationary. Geostationary means as the Earth rotates, the satellite will rotate together. So what I have here is an example of a geostationary satellite. You imagine a human standing here, okay? Whenever it looks up to the night sky, this satellite is always on top of the same point of the Earth. There are two different geostationary satellites. Maybe this is on top of country 1, maybe this is on top of country 2, and they rotate at the same orbital or angular velocity as the Earth. Okay, this is how it appears to remain above the same point. So in order for that to happen, we need other features as well. So the first feature here is it has the period of 24 hours. This is the first one. Feature number 1. Okay. Feature number 2 for geostationary orbit is that it must rotate from west to east. If you think about how the sun rises from the east and sets from the west, it means that the Earth is rotating from west to east. Okay? You record a lot of TikTok, you will know what I mean. The direction is flipped from the perspective, okay? So basically, the satellite will have to rotate in the same direction as the Earth, and the Earth rotates from west to east, and we know this because the sun rises from the east and sets in the west. Okay? Number 2, it also must appear, it must be in equatorial orbit. Equatorial orbit. Meaning to say, if let's say you have a 3D planet, or let's say if I have a 3D sphere, I'm going to try to draw a rough sketch of a sphere. So if I have a 3D sphere like this is my sphere, okay? There are many possible equators. Of course, the main one is the geographic equator. So the satellites must be here. It can also be along this. These are all equatorial orbits. Because there are infinite equators along the circumference. So there are various equatorial orbits. Non-equatorial orbits are like this one. Okay, this one here, this one here. So this is not equatorial. So the equator is defined as the thickest part of the sphere. And because the Earth is a sphere, there are many, many thickest parts. So 1 mark each. You just need to roughly know the features of geostationary satellite. If you're interested, there are plenty of things that you can find, very deep dive into the internet. And I think now it's relatively cheaper to send a satellite. You just need to be a millionaire. You don't have to be a billionaire. All right, anyway, in part 2, the mass of the Earth is given. Okay, so this is our capital M. Use the expression in A, which is the one we derived just now, to determine the radius of the geostationary orbit. So even if you cannot prove this expression, you are more than welcome to use it. My friends, they give you so that even if you cannot prove, you can still use. That's the intention of giving you the equation to begin with. If they allow me to move it here. Okay, there we go. All right, so we're going to use this equation. A bit stretched. So I want to find the radius, and what I normally do is I rearrange first because later I need to press calculator. Okay, so I will have r cubed because we are looking for r. So r cubed will be equal to gm t square over 4 pi square. Okay, this is a pro move. You arrange first, then only you substitute. That way you don't have to move big numbers around. Anyway, gravitational constant can be found in the table of constants. So this is 6.67 times 10 to the power of negative 11. You know the mass of the Earth, 6 times 10 to the power of 24. And the period, they already mentioned geostationary orbit. So the period is 24 hours. Now here is where you should hear a CD scratching sound in your brain. Wait. We need to convert to SI. Yes, we need to convert to SI. But Miss, why? Why we need to convert to SI? Because you have a VVIP in the house. I mean, in the equation. This is your VVIP, your gravitational constant. So whenever you use a physical constant, it's like a VVIP, you know? You open the physics paper, the first few pages got their name already. This is VIP, right? When you open the agenda, you see people's name there, you know, that one is VIP. So this is the VIP or the MVP, okay? So whenever you have a physical constant, I don't care whether it's the universal gas constant, gravitational constant, any kind of constant, you have to convert everybody else into SI, okay? So this is a physical constant. Okay, so all other units are SI. Unless you have a way to cancel off the non-SI unit. And in this case, that is not possible. All right, so that means this 24 hours have to convert to second, which is 3600. You need to times 60 2 times to change from hours to seconds. Okay, so this part is for those who need it. Okay, this is hour to second. Okay, I think we can proceed now. This is 4 pi square. Don't forget the r cubed though. So here's a confession. I sometimes forget to square root and cube root. I am that person. So to prevent myself from making these kind of mistakes, what I normally do is I will write r cubed and I will write r like this. So this is one of the way I write my answers before I pull out my friend the calculator. That way, if I make a mistake, it'll be a bit more obvious, hopefully. Okay, so the reason why I pull out the calculator is because kind of want to teach you how to press the calculator lah. Okay, so the reason why I encourage rearranging, then only showing substitution is because now you can press the whole thing in your calculator and you don't have to keep transferring prefix. The more you transfer, the more painful it is. So this is 6.67 times 10 to the power negative 11, your gravitational constant, multiply by 6. So you notice that whenever there's times 10 to the power, I use this button here. Times 10 to the power of 24. Okay, even if you use a different version of a calculator, there should be a E, large letter E, or some buttons like this at this point. Okay, anyway, where were we? This one. Okay, and then multiply by 24 times 3600. Okay, divided by 4, divided by pi square. All right, so I'll press equal. So this is r power 3, 8.759. So I'll write that times 10 to the power of 8.759 times 10 to the power of 17. Okay, so it is possible to press the whole thing in your calculator. All right, cube root, what do we do? Well, I see a cube root here, so I'm going to shift like this. Answer, or you can answer power 1 over 3. So the answer is 9.567. So 9.5. I'm going to keep this to 3 SF. So this one is 9.57. Yes. Times 10 to the power of, okay, here's a cool thing. You see this ENG button? You can press again. So the ENG button will help you move lah. So this is 9.57 times 10 to the power of 5. Okay. Just direct substitution. Oh, wait, into the equation. Some of you are like, no, miss, you've forgotten the square. Correct. I'm also showing you what's a common mistake because mark countless papers will see this all the time. How do you check whether your answer is correct? If you have any kind of like familiarity with numbers or magnitude, right, you will notice that this is way too small. Miss, how do you know this is way too small? Because I do enough questions to know that the radius of the Earth is 6,400 kilometers. Okay? Or in other words, it's 6.4 times 10 to the power of 6 meter. You mean this thing is so close to Earth? Not even the radius? Cannot be right. Okay? So where is the mistake? If you're like making a lot of noise in your brain because you think that the square is missing, great. You're right. The square here is missing. Hiya. So what to do during exam? Well, don't worry. Cancel off this one. Cancel off this one. You don't have to redo everything again, please. Hopefully you haven't pressed all cancel in your calculator. Your calculator looks like this. And then you're slightly annoyed, but you're not that worried because you can press the rewind button. It's rewind time. I mean, you are watching this on YouTube after all, right? Okay, so what I can do is I go back to here and introduce a square. Okay, boys and girls, ladies and gentlemen. So if you introduce a square here, then you really don't have to do anything much after this. So this will be 7.567 times 10 to the power of 22. 7.567 times 10 to the power of 22. And a different way to cube root something is to type this x to the power of 1 over 3. Up to you lah. Okay, so from here, I'll get a different answer. Let me toggle the ENG button. So this is 4.23 times 10 to the power of 7. 4.23 times 10 to the power of 7. Cancel this one off. 4.23 times 10 to the power of 7. Okay, so I make it a point to show you how to correct your mistakes and how to spot them. Whenever there is power and you transfer a lot of number, maybe in the process of converting your period, you may have forgotten that you need to inherit the square. Okay, so if that happens, just always go back and double check your working and ask yourself, do my answer make sense? Okay, now this makes sense. You know why not? Because this one is so small. So your satellite 10 to the power of 5 is too small. Okay? What does this mean? Satellite in Earth, because the Earth radius is already 10 to the power of 6. So 10 to the power of 5 is actually on the surface of Earth. It's very weird. Inside, you dig a hole. Cannot. Okay, that is not called a satellite, that's called a underground rover. Alright, so always think about your answers, double check and make sure that they kind of make sense. Alright, and also there's a lot of traps when it comes to power 3 and also power 2. So just do slowly lah and double check. Alright, so that's part 2. And I showed you how to make correction without taking too much of your time. Okay, so a good habit in your calculator is don't go answer already and then just cancel everything. You cancel everything or then set liao lor, can still go back. Sometimes cannot go back already. Okay, so if you don't cancel, just leave it there and then re-examine your working again. Okay, part C. A global positioning system, GPS satellite, orbits the Earth at the height of this much above the Earth's surface. So this is also another tell that your prefix is 10 to the power of 7 because of the km. Okay, so if you get 10 to the power of 5, you should already sus already. All right, so 10 to the power of 4 km above the Earth's surface. The radius of the Earth is there, they give already 6400 km. Okay, use your answers in B2, which is the mass of the Earth, not the mass of the Earth, the radius of the orbit, and the mass of the Earth if you need it, and the expression of this, to calculate in hours the period of orbit of this satellite. Okay, let's draw a drawing to help us brain the question. Okay, so here what we have is we have Earth, right? Earth in the middle. I'm going to label this as our Mother Earth. Okay, you will have two satellites. One is pretty far away, right? 4.23 times 10 power 7. So this is the radius of orbit, my friends. Okay, radius of the orbit. So whenever we look at the radius of the orbit, where are we measuring? We are measuring from the center of the Earth. You know what? This is a nicer picture. I'm sticking to this one. Okay, so we have the radius for this. This was 4. Brain hang, cannot remember. 4.23 times 10 power 7. Okay, and now we have a second satellite. Okay, we need to read the question carefully, okay? So this first satellite, okay I measure here, will be measured from here to the center of the Earth. All the equations that we use, whether it's centripetal force or gravitational force, has to be measured from the center of the Earth. And this is 4.23 times 10 to the power of 7 meter. No problem. Now we have 2.0 times 10 to the power of 4. Now, if you're very tempted to use this as your R, this is not the radius of your orbit. Miss, how you know? You see, they so sneaky. They say above the Earth's surface. Hiya. And then you have radius of the Earth. Hiya. So that means your value of R, you need to add these two numbers together. Okay? So let me draw a zoom in version of what is happening. This is the center of the Earth. Okay? This is the radius, 6.4 times 10 to the power of 6 meter. And then you have another satellite, IDK where? Let's draw here. This is my satellite. And this is the circular orbit. And here to here, my friends, is your 2.0 times 10 to the power of 7 meter. So what is the radius of your orbit? The radius of your orbit is actually the whole thing. Okay, whenever we measure radius, we always measure from the center because the mass of the Earth is concentrated at the center. Yeah, if I don't see this, then GG lo, exam correct. Correct. Okay, so I'm gonna consider the radius of the GPS satellite. R, I'll call this big R. Okay lah, call this R2 lah. R2. R2 will be 2.0 times 10 to the power of 7 meter above the Earth's surface. So we need to add this 6.4 times 10 to the power of 6 meter. So what I'll get here is 2.64 times 10 to the power of 7 meter. Because, you know, if I change this to 10 to the power of 7, I move the decimal point, becomes 0.64. Okay? So this second satellite is actually here, measured from the center. I mean, not drawn to scale, obviously. This is 2.64 times 10 to the power of 7. So the circle is, one circle is here, and the other circle is here. Okay, so you got two different satellites at different orbits. Yeah. All right, so now we have this relationship. In fact, this is your Kepler's third law. No, here, see? T square proportional to R cube. So you will encounter T square proportional to R cube in many various formats if you try out the past year question. Okay, so I'm going to use this expression directly. They didn't ask me to prove. If they ask you to prove, you just continue from this expression. You start from here, and then you just add the sentence. Since m is constant, you don't have to tell people that g and pi is constant, okay? So t squared is proportional to r cubed. Okay, but they give you already, you use directly. So t squared is proportional to r cubed. Depending on how you do proportionality, so I'll probably do this in a slower way for the first time. T1 square is equal to k r1 cube. T2 square will be equal to k r2 cube. Okay, so they are the same constants. That's why we can use proportional. And then I will take equation 1, divide by the equation 2. So I can cancel off the k. What I have now is T1 square over T2 square is equal to R1 over R2 cube. Ratio is your best friend. Okay, so certain students, they will straight away jump to T1 over T2 square is equal to R1 over R2 cube because of this relationship. Okay, that is perfectly fine. Okay, so I'm going to substitute the period. The first period is 24 hours. I'm going to put 24 here. Miss Ken meh? I thought you say need to convert. Are you chill first? You ask yourself, did we invite the VVIP, gravitational constant? Okay, we are looking for the period. Calculate in hours the period of this satellite. So we are actually looking for T2. Okay, I'm going to put T2 here. This one is square. Okay, what is the first radius? The first radius for 24 hours is the green color pathway, or your answer in the previous part, which is 4.23 times 10 to the power of 7. Okay, and the second radius here, second radius is 2.64 times 10 to the power of 7. Don't forget the power 3 law. Okay. Is there gravitational constant? No. Does it matter if there's gravitational constant? I mean, does it matter if you change or you don't change? No, because the units cancel off, you see? Meter and meter, these two will cancel. And T2 will take whatever unit that the 24 hours is. Okay. So from here, what we can do is we can, I guess, press our calculator law. So 24 over T2 will be equal to, okay, so again, when it comes to pressing calculator, I'm using the normal linear mode because I know not everyone has this version of the calculator. But if you have that fraction mode, you can use that as well, as long as you're comfortable, lah, friend. You know what, 10 to the power of 7, no need to press also can. So this 10 to the power of 7 will cancel off, so 4.23 divided by 2.64. to the power of, okay, 3. And then you bring the 2 here, so divide by 2 lor. Okay, square root 1 over 2. Okay, so I get this one, 2.028. And now I can find T2. T2 would be 24 divided by 2.028. And that should give me 11.8 hours. Okay, so this orbit will be slower and it is definitely not geostationary lah. So GPS used for tracking and also used for navigation. Okay, so you can see from a conclusion here that this GPS is not geostationary because it's 11.8 hours. All right, so that's it for this question. What did we learn? We learned, number 1, that most of the time, whenever we are proving some random expression, we can always rely on this relationship. Gravitational force provides centripetal force. Okay, so make sure you show all the key steps. Number 2, there's this thing called a geostationary satellite, meaning the satellite will always appear to remain above the same point on the Earth and has a period of 24 hours. Okay, so these are the properties of geostationary satellite. Then after that, we do some calculation. So here there are some techniques that I more or less introduce to you because just want to make sure you don't make those mistakes. Okay, so I make them here for you. Number 1, whenever there's a power 3, power 2, be very careful and make sure it follows along the way. And remember to cube root. Number 2, rearrange everything first and also make sure you convert the unit whenever there is a physical constant. Number 3, when it comes to square, if let's say you miss out halfway, don't worry. Part of life is making mistakes. So check your answer always. Does it make sense? This one makes sense. This one does not, because this value is too small. The radius of the Earth already 10 to the power of 6. If the radius of orbit is less than radius of the Earth, is the satellite on Earth, underground? Okay, so then check your working. Maybe you forgot to convert. Maybe there's a square there somewhere missing. So learn to develop a good sense of numbers. All right. Then the last part here is proportionality. You will be still using this technique throughout your paper 4. You have done this in your paper 2, hopefully, some proportionality relationship. We will repeat them again. And there's geostationary satellite, mainly used for communication or watching football matches before the lockdown. Okay. And there's also non-geostationary or GPS satellite, normally used for spying or tracking. Okay. Or let's say, for example, you're a millionaire and you have a satellite phone, then the satellite phone comes with a satellite. So satellite will follow you everywhere you go. Rich. That is all for this question. All right, now see you in the next one. Remember, don't make power mistakes.